Very quick. Hey, question 6 then. This is about this is partly from the acids topic. So we're talking about hydrochloric acid, which you should all know is HCl, and we should know that hydrochloric acid is a strong acid, which is what it tells you here anyway. So let's just go ahead and get this. So when it's not dissolved in water, hydrochloric acid, or hydrogen chloride we call it, looks like this. Hydrogen's got 1 electron in its outer shell. When it's an atom, and chlorine, it's got 7 in its outer shell. We know that because of the groups that are in the periodic table. So when they combine, they must combine to make 1 bond. Hydrogen always makes 1 bond, and chlorine always makes 1 bond, because they can both fit 1 more electron in the outer shell. And so when we're drawing the dot cross diagram, start by drawing the stick diagram. There must be 1 bond between them. 1 bond, 1 line, represents 1 pair of electrons. So you've got 1 mark for drawing 1 pair of electrons between them. But then you have to draw the other electrons that were in chlorine's outer shell, and usually we draw those at 12 o'clock, 3 o'clock and 6 o'clock in pairs, but it doesn't really matter if you spread them out. Okay, so 2 marks, 1 for that, 1 for the rest of them. And hydrogen's got no more, right? When you dissolve hydrogen chloride in water, it turns into hydrochloric acid, which is a strong acid. It's a strong acid because it fully dissociates or ionizes to release. You don't need this for the mark, but to release H plus in solution. And so again, you don't need this for the mark, but you've got HCl, when you put it in water, fully breaks apart into H plus and Cl minus. And that's different to a weak acid. Weak acids only partially dissociate. You kind of got an equilibrium set up with a tiny bit of H plus on one side and the acid on the other side. So how can magnesium be used to distinguish between a strong acid and a weak acid? So hopefully this is a little practical you've done. If not, ask if you can maybe have a look at this. But if you take some, you should know that magnesium and acid reacts to fizz and gives off hydrogen. So it fizzes. But a strong acid, if you've got the same concentration strong acid as the weak acid, the magnesium plus acid reaction will fizz much more in the stronger acid. That's what's going on here. So it's all about the fact that it's fizzy, or the disappearing, or you might have just said, or the disappearing, oops, you don't spell it like that, do you? Disappearing of magnesium happens at a much faster rate in the strong acid. It's actually very slow in the weak acid. Weak acids are much slower to react. Okay. So the concentration of an acid is increased by a factor of 100. Now I'm just going to remind you of what's going on here. So if we have this pH scale, which you know goes 1, 2, 3, 4, 5, 6, 7, all the way up to 14. This is the typical rate. You can actually get acids that are slightly outside this range, but more or less acids go from 1 to anything up to 7, which is neutral, and then you've got alkalis above 7, right? And pH, remember, pH is a measure of the concentration, of hydrogen ions in solution. The more concentrated the H plus, the lower the pH. And you also have to remember that there's a 10-fold or 10 times change in concentration of H plus gives you a 1 unit pH change. This is a so-called logarithmic scale. So if you go, say, from pH 4 to pH 5, that means you've got a 10 times increase in concentration of H plus, or if you go from 5 to 3, it's 100 times increase in concentration of the H plus. So each 1 unit pH change is 100 times change in concentration. Sorry, each 1 step pH change is a 10 times change in concentration of H plus. Right, so this is, so as HCl is a strong acid, the the H plus concentration is the same as the hydrochloric acid. If you increase it by a factor of 100, it's a twofold 2-unit change. But you had to really, to get the mark, say, I'm just going to check the mark scheme, but yeah, you've got to say it decreases by 2. So 1 mark for saying it's a 2-unit change, 2-unit pH change, and you get the mark for saying that it's a decrease in pH. Now, easy to forget that one, but of course you know that this is the strongest acid. This is the weakest acid about here somewhere, right? Let's do question 7 as well then. A reaction about elements and compounds. You've got the reactivity series with things like potassium very high at the top, way down to copper, and you've even got things below that like gold and so on. You're expected to work out, using this, how to extract a metal Y from its compound. So I'm going to remind you that you've done this, you've learnt this about iron. How would you extract iron from its oxide? You do that by reacting it with carbon, which is higher than iron on the reactivity series. So carbon displaces iron from a compound because carbon is more reactive than iron, right? You can't do that with metal Y because metal Y is more reactive than carbon. So it might be something like aluminium, which is more reactive than carbon. So in those processes, you have to use electrolysis. Right? Electrolysis is the process which is it's kind of a much more powerful method of extracting a metal from its ore. Now, electrolysis only works if the substance, the ionic compound like aluminium oxide, for example, can conduct electricity. It's an ionic compound, remember, so it has to be molten. So a lot of you forgot to say that it has to be a liquid, in a liquid state to extract it. All right. You could, as an alternative mark, say heat it with a more reactive metal or heat it with potassium. So heat with potassium, for example, would also get the mark. Because that would work. It'd be a crazy thing to do, but you know you could do it. Alright, that'll do. Moving on. And then the next one is simply complete a balanced equation. So this is an example of a displacement reaction because you've got sodium, a highly reactive metal, displacing titanium from titanium chloride, a compound, and that gives you titanium. So that will give you sodium chloride as a product. Now, sodium is in group 1 plus, so it forms a 1 plus ion, and chlorine is in group 7, so chloride is a 1 minus ion. So the formula of sodium chloride, as you know anyway, is NaCl. It doesn't matter which side you write it, I'm going to write it there though, and you're told the other product that's produced is titanium. And metals, we only ever write them as they are. So you got a mark for highlighting that the two products are titanium and NaCl and getting the formulas right. But that's not balanced at the moment, you've got to balance it. So I'm going to go through the method of balancing that you were taught way back in year 7 or year 8 or whatever, by just counting the number of each element on each side. So sodium, titanium, and chlorine, sodium, titanium, and I'll squeeze it in here hopefully. I put it over there because I couldn't squeeze it in. But sodium is 1, titanium 1, chlorine 4, sodium 1, titanium 1, chlorine 1 at the moment. So I need 4 chlorines on the right, otherwise it's not balanced. I'm going to stick a 4 in front of it over here, and I'm going to count again. I've got 4 sodiums and 4 chlorines now. So I've fixed the chlorine, but I've messed up the sodium. I can fix that by putting a 4 in front of the sodium there. That's it, job done. So you get the second mark for balancing. And then you have to show the half equation showing that sodium is oxidized. Now I know that this is tricky. This is going to take some practice between now and the exam, but you are going to get half equation questions. So half equations just show what's going on in redox reactions, in other words, oxidation to reductions. They show the oxidation separately from the reduction. So remember oil rig, oxidation is loss, so it's be loss of electrons, and this will be gain of electrons. So it tells you here we've got sodium being oxidized in this reaction. So this must be some sort of loss of electrons from sodium. So you start with sodium, and we've got sodium chloride as the product, in other words sodium ions and chloride ions. So sodium turns in to sodium ions. Now if you think about it for a sec, sodium has got, if you look at the periodic table, it's got 11 protons and therefore 11 electrons. And sodium ions though are 1 plus. So it must have lost an electron, or there is an electron missing, like just 10 electrons here, and this stuff's got 11 electrons. So to get from here to here, it must lose an electron. So we write that over here. Right. So sodium, when it turns into sodium ions, loses an electron. That's all that's showing. That may well need a little bit of practice. That gets 2 marks if you've done that. You've got 1 mark for well, I don't know how it's marked. It just says here you get 1 mark or 2 marks for the right answer. So you got 2 marks for getting it right. There we are, just moving on. So then finally calculation question. You got this calculation question. That's really straightforward to use, an absolutely standard method for this. So you've all been taught the same way how to do these kind of reactive mass calculations. What is slightly tricky here is you have to determine the limiting reactant. And if you didn't do that in the way they wanted you to, you didn't get the marks. I'm going to turn my light on for a bit more light here. Right, so let's go through the process. So the first thing to do is just to write out the balanced equation. Personally, I just like to have it written out. I'd encourage you to do the same. If you do, you'll get into good habits and you'll pick up, AlCl3. So you pick up easy marks when you start to set it out properly. So you fill in your table with what you know. So the molar ratio is simply the number, the coefficient, the number in front of the chemical. So 2 to 3, that's a 3 to 2. Okay, so 2 to 3 to 3 to 2. And then we fill in what we know. So we've got 108 grams of aluminium, so mass. We always write the mass in grams. We must write the mass in grams here. You've got 1.2 kilograms of copper chloride. You must convert that to grams. So that's 1210. And you've been asked to work out how much copper is produced. You need to work out this here. Right, so with any of these, the thing to do is to try to work out the number of moles. And if you've been given mass, you can work out the moles by using the MR. Now, technically, this is the mass of 1 mole, so you can have that in grams per mole. Now, when you're doing the MR or the formula mass or the atomic mass, if it's just an element on its own, the thing to do, trick that I do, is to put a box around the chemical, so just to force you to ignore the number in front when working out the MR. Look at the periodic table. There's 1 aluminium. In the periodic table, aluminium is 27, and copper chloride, if you add the copper, it tells you here, 63.5, add the 2 chlorines, it's there, it gives you 134.5, that's too easy, 134, you don't have to work that out, it means you don't get a mark for it. You then have to work out the number of moles, or N in moles. The way to work out the number of moles is N is equal to the mass. This is one of the very few equations you have to learn. Okay, is that. So the moles equals mass divided by the MR. 108 divided by 27 is equal to 4. And that's your first mark. 1210 divided by 134.5 is 8.996, and that's your second mark. So we're picking up some marks now, and then you did get the mark if you wrote 9, by the way, or you should have done if you wrote the number 9. So you then have to work out what the limiting reactant was, and you did have to use a particular method for working out the limiting reactant. So you have to work out how many moles of copper would be produced either by using 4 moles of aluminium or 9, let's say, moles of copper chloride. Okay. Now, let's start with the copper chloride. So if we had 9 moles of copper chloride, there's a 3:3 ratio, so that would leave you with 9 moles of copper. But if you had 4 moles of aluminium, let's plug in my computer. Okay. If you have 4 moles of aluminium, it's a 2:3 ratio, or a 4:6 ratio if you like. So from 4 moles of aluminium, you'd get 6 moles of copper, right? So the limiting reactant out of these two is the one that could produce the least amount of copper. So it doesn't matter if you could chuck in loads and loads and loads more copper chloride, you'd get no more copper produced, because this is the limiting reactant, right? And so therefore, so you highlight that as the limiting reactant for a mark. And really you should state in words that 9 moles of this would give you 9 moles of this, and 4 moles of this would give you 6 moles of copper. So limiting reactant is aluminium, and you have to show your working there annoyingly, but you get a mark for getting that right, and a mark for showing what they produce, which is 6 moles. If we were to work out the formula mass of copper, which is given to you as 63.5, the mass is equal to just a rearrangement of this, so the mass is equal to the mR times the number of moles, so 6 times 63.5, and that comes to 381 grams. Now you didn't just get the mark for getting the right answer, you have to show which is the limiting one in a previous part of the question. So really explaining the limiting reactant is worth 2 of those marks, I would say. Right, moving on. Why does sodium conduct electricity? So straight from, oh, by the way, there are other methods of doing that, the question I've just shown you, but that's the one I'd encourage, right? So for this one, you've got to mention delocalized electrons. They can carry charge through, underline through rather than throughout the metal. In the and that's it. That's what we've got to say. Under what circumstances can sodium chloride, which is a metal and a non-metal, so it's ionic, under what circumstances can that conduct? Well, first of all, you're expected to know that it doesn't conduct when solid, because the ions can't flow, but it does conduct when molten, or liquid. Molten just means liquid. If you heat it up enough, all the ionic bonds in the lattice structure break apart, and the ions, the sodium ions and the chloride ions, can just swoosh around, and they are free to move. So you get a mark for saying it's molten, a mark for mentioning that it's ions then that are free to move around. There we are, that's a good place to stop.